Hello friends, I welcome you to our ongoing Six Sigma journey, and I would like to remind you that we are in the analyze phase of DMAIC cycle. We have completed define, we have completed measure phase, and now we have started the analyze phase with hypothesis testing concepts and the examples. So, if we just revisit our inspiration, that science is advanced by proposing and testing hypotheses, not by declaring questions unsolvable. So, here we must appreciate that any organization, company, if they want to say test a theory about a market, about a consumer, about a product, or they want to propose a new theory, they cannot just do it on a trial and error basis, arbitrary. They need to test it scientifically, and the scientific way is to check your claim, which is the hypothesis, through a statistical analysis. So, in this particular lecture 29, we will apply the concepts we have studied in the previous lecture on hypothesis testing, and we will solve couple of interesting examples on hypothesis testing single population test. So, this will give you a feel of real life application of the hypothesis testing and how the concepts we have seen in the previous lecture could be applied for a real life situation. So, in this lecture we will focus only on single population test. It means you are basically interested to verify your claim for a single population, and this population could be a territory, could be a gender, could be a kind of particular product and its production and so on. So, we have basically talked about some of the very important concepts in the previous lecture. What is statistical hypothesis? It is basically your claim. What is null and alternate hypothesis? So, null hypothesis basically dictates the status quo. It means this will happen, and alternate hypothesis says that this will not be true, this will not happen. So, we had seen this concept. Then there was a very important concept, type 1 and type 2 error. I would like to remind you that all the statistical analysis, basically we try to draw the inferences based on sample, and ultimately there is a chance phenomena, there is a random phenomena, and the probability associated with this chance or random phenomena cannot be ignored. So, I cannot say that I am 100% sure that this claim is accepted or rejected. I can only say that at some level of significance alpha and the type 2 error beta, I would accept this claim or I would reject this claim. So, we had a good discussion on type 1 error and type 2 error, and as I mentioned that selection of the type 1 error and type 2 error, these are inevitable, you have to accept, but you choose the appropriate level depending upon the situation and its impact on making the wrong decision through inferential analysis. So, you have general steps in testing the hypothesis, and there are basically three approaches for hypothesis testing. Approach number 1, critical value approach. You get the value from a statistical table. This is the critical value, which we call it as a theoretical or tabulated value, and all the statistical tables are developed using the probability distribution function of a particular say distribution, and for the convenience, for the ease, we have these ready-made tables available that we can refer to get the critical values, so that we can make a decision whether accept or reject about our claim, which is null hypothesis and alternate hypothesis. You have approach 2, this is p-value approach. We had seen the merits of this approach. It is more intuitive to the managers because it expresses the probability of rejecting or accepting the null hypothesis and how far we are, our observed level of significance, which is the p value, how far we are from the accepted level of significance for testing the hypothesis, that is alpha. And approach C is the confidence interval. I want to check that on an average, suppose I have 95% confidence interval, then my particular value or my null hypothesis will be true for which particular interval if I have to check it for 95%, 99% or 90% confidence interval. So, we had cleared our basic concepts. Now, this lecture typically will is devoted on solving couple of real life examples to help you to appreciate the application of hypothesis testing typically for a single population. So, we will see hypothesis testing for a single population using Z statistic, using T statistics and for proportion. So, I would like to repeat the general steps we follow in hypothesis testing. So, you state the null hypothesis typically called H0. Suppose in the pink box right hand side I put it as H0 mu is greater than or equal to 3. State alternate hypothesis, so I will say mu is less than 3. So, here it could be 3 kg. You want to fill the material in the bag. It could be the average of the score, whatever may be the problem. You say that my mu is greater than or equal to 3, or alternatively mu is less than 3. So, my alternate is H1. Now, you choose the alpha value depending upon the severity of the say decision or consequences looking to the particular situation you are investigating. To remind you, suppose if I punish an innocent person, then the alpha value chosen, if it is too high and if I punish the innocent person, there would be a great societal loss as well as lot of consequences. But it is okay if I by chance make a wrong decision and declare a guilty person innocent, fine, again there is an error, but the societal consequences are less, and later on because this person has certain traits, definitely I can triangulate, I can verify, or this person will make another mistake and there is a probability that he will be caught. So, if nothing is given or you do not have much confidence in understanding the impact of making wrong decision, then as a rule of thumb we feel comfortable with alpha is equal to 0.05. Choose n is equal to 100, just it may be 100 or 50 or 150. Choose test, I am choosing here Z test, let us say. This is just the description of the general steps of hypothesis testing. Then number 6, set up the critical value. So, once you have the alpha, you refer the statistical table, and for the given alpha you will have this particular critical value. Here it is minus 1.645 for your alpha is equal to 0.05. So, then you collect the data and compute the test statistic p value, make the statistical decision and express the conclusion. So, here for this particular example you can see that my alpha basically is alpha is equal to 0.05, and if I conduct the two-tailed test, it means I consider the both the sides, suppose then alpha by 2 would be 0.025. Now, if you see my p value corresponding to computed test statistic minus 2, then it comes out to be 0.0228. So, this value is basically falling in the rejection region because it is 0.0228. So, 0.0228 is less than 0.025. So this is a probability value. So you can say that some region here will be your p value, and as it falls in the rejection region, you will reject the null hypothesis. So this was the example about the true mean number of TV sets less than 3. So I accept the alternate hypothesis. Now we will see more examples to make the idea clear. So just see, as I mentioned, that you can have one tail test as well as you can have two tail test. When I say one tail test, you are only interested either in the lower side or lower tail of the distribution. It is a normal distribution, and if I say higher or value, then if I am interested in the right side tail higher value, then this is again a one tail test, this is again a one tail test. So maybe my interest would be either on the left side or right side, and I may conduct only the one tail test. Alternatively, I can go for say two tail test like this. So here I am interested in both side alpha by 2 and alpha by 2, and I will compare my computed statistics and the p value with this level of significance alpha by 2, and if it falls within, then I will say my null hypothesis is basically in the reject because my value p value or critical value is falling in the rejection region. But always remember, we reject or accept the null hypothesis or accept the alternate hypothesis at a given level of significance, and we have to accept of committing type 1 and type 2 error, because inferential statistics is for a chance phenomena, random phenomena, and when I deal with the probability, then I have to accept of making a wrong decision, the probability of making a wrong decision, as well as say probability of rejecting the null hypothesis or accepting the alternate hypothesis. So this is something that we try to do in hypothesis testing. Now let us try to consider hypothesis testing for a single population mean using Z statistics. So we had seen it previously that there are various types of distributions, and you have the associated probability distribution function. This probability distribution function is used to develop the statistical table, and for each particular distribution you have the statistical table for ease in computation, getting the values corresponding to your computed statistic. So you have normal distribution, and for standard normal we refer the Z statistic. When I say standard normal, then my mean is 0, my standard deviation is 1, and I refer the Z statistics and the Z table. So here let us say we want to do the analysis with the Z statistics for mean, and my assumption here is that sigma is known. It means sigma is for population, and I know that what is the population standard deviation. So population is normally distributed. This is my say first assumption. Population is normally distributed, then if not normal requires large samples, and null hypothesis has less than or equal to or greater than or equal to sign only. So my Z statistic basically is x bar, that is your sample mean, mu x bar, this is your population, and sigma x bar, this is your sample standard deviation. So here I will use the central limit theorem. So I will say x bar minus mu divided by sigma square root n, as I am making use of the central limit theorem. So this is the expression that I can conveniently use for computing my values and comparing the values with the critical values obtained from the table. So just see that I have typically a rejection region, and here let us say I am talking about one tail test. So I can conduct the one tail test either for the left tail or for the right tail. Just see, this is the left tail and this is my alpha, which is level of significance and also type 1 error, and what I say that Z must be significantly below 0 to reject null hypothesis. So it should fall in this particular region as shown by the arrow, and then I will reject the null hypothesis for this one tail test when my region of interest is on left tail. Now here you can see that you have this Z value, and again your distribution, this ranges from minus infinity to infinity plus infinity. Here also it is minus infinity to plus infinity, and you have this particular region that is of interest, and I would say that small values of Z don't contradict H0, don't reject H0, or else you should have the value of Z which falls in this particular region, so that you can reject your claim status quo, that is the null hypothesis, and you can accept the alternate hypothesis. So here you have this single tail. So let us try to see the example for one tail test, and the question here is that does an average box of cereal, you are purchasing various kind of cornflakes and oats and other things. So cereal contain more than 368 gram of cereal. So fine, there could be variation in packaging, but obviously company would not like to fill the excess or too less, which will basically either disadvantageous to the company or to the consumer. So they want to check that on an average, suppose if we fill this much, then whether we are significantly lower compared to our value or whether we are in the acceptable zone. So a random sample of 25 boxes showed that 378.5 is the average, and 368 gram is the actual content that should be there. So the company has specified S to be 15 grams, and S is your basically sample standard deviation, and they want to check their claim at alpha is equal to 0.05. So now my null hypothesis here is M is equal to 368, that on an average I am filling up 360 grams, 8 grams of cereal in a box, and alternate hypothesis is that I am filling up 360. So now here you would say that it is very much visible that 372.5 is greater than 368. What is the need of conducting this analysis? So I would like to remind that there is descriptive analysis, there is inferential analysis. Descriptive analysis, yes, I get an idea that 372.5 is greater than 368, but this is a chance phenomena, this is a random phenomena. I have taken a sample and I want to check at a given level of significance alpha is equal to 0.05, that to what extent my claim that I am exactly filling 368 or greater than 368 is really true. So inferential statistic provides more scientific basis when you are not actually becoming clear just with the comparison of values that you do through comparison of various measures of central tendency or measures of dispersion. In descriptive statistics, we try to check our claim with more rigorous process scientifically, and that is where I make use of inferential statistics. So here you have this particular say hypothesis. Now I want to check it. So procedure is very simple, and what you need to do, just see, you have alpha is equal to 0.05, and first I need to identify this particular value. So for this level of significance, what is the tabulated value in Z table, statistical table or theoretical value, and this value is called typically the critical value 1.645. I can just give you the little snapshot of the table here, and your full table you can see in the statistical books suggested. Here it is just a small portion, and you can see that I have z value 1.6 and here it is expressed in decimal. So I want to find the alpha is equal to 0.05. So you have alpha is equal to 0.05. So now for alpha is equal to 0.05, you want to find out the value of this, and it could be 1.65 or little bit you can average it out. So it would be say 1.645. Averaging is required because my level of significance is 5% and hence this value is 0.95. So if you see here, it is 0.9505, it is 0.9495. So if you little bit do averaging, then it would come out to be 1.645. So this is my critical value. I want to test my claim, null hypothesis and alternate hypothesis against this critical value to check that to what extent I am right in my claim or I should reject the null hypothesis. So this is how to read the statistical table. Already we discussed previously. So my null hypothesis is H m is equal to 368 and m is greater than 368, alpha is equal to 0.5, n is 25. So now this is my critical value and this is my computed value. So for computed value you can just make use of this particular expression, x bar minus mu divided by sigma divided by square root n. You just plug in the values, you have all the values given in your data set and you can compute this 1.5. So 1.5, because I am say computing with reference to this 0, 1.5 is in this region, this is the region and this region is basically my accept region. If it would fall in this region, it is my reject. So I would say that when I compare 1.5 with 1.645, 1.5 is less, so it would fall in the accept region, not in the reject region, and I do not have enough evidence to say that mean is more than 368. So the conclusion is that do not reject at alpha is equal to 0.05. So is it not interesting? Visibly, if you will say, then because it is 372.5, so if you just see this, then you have 372.5 as the mean of your 25 units, it is a sample, and by observation without statistical analysis you say that 372.5 is greater than 368. But when you check it with scientific basis, hypothesis testing, you come to the conclusion that do not reject at alpha is equal to 0.05. So my conclusion is that there is not much evidence, significant evidence available that true mean is not 368. Okay. So this is something that we have seen about two-tail. We can also do, so this is we have done for one-tail test initially, and now we would like to also do it for the two-tail. So initially I just explained you this particular part. So do not reject my, I will just go back. Okay, this was the table. So do not reject at alpha 0.05. Now p value is 0.0668, and if I go by even the p value, I would get the same result, that do not reject null hypothesis. Now this is exactly what, that your p value is 0.0668. So 0.0668 is greater than your 0.05. So basically your total probability region is given by this and it is larger than the alpha. So, I will say that do not reject null hypothesis. Now, let us go ahead. For the same example, I want to do a two-tailed test. So, I have, let us say, an average box of cereal contained 368 gram, and again I took the random 372.5. The company has specified S sample standard deviation to be 15 gram and test the hypothesis at alpha is equal to 0.05. So, I am setting here, say M is equal to 368 and alternate hypothesis you just put this not equal to 368. So, you put here M is not equal to 368. So, now I want to test my claim for this particular situation. So, let us say H0 is M is equal to 368, M is not equal to 368 and my critical value is 1.96. I am referring to two-tailed test. So, this is minus 1.96 plus 1.96. You just plug in the value. We have already seen Z is equal to 1.5. Now, again I will end up with the same decision because minus 1.5 is less than this, and I will say that do not reject at alpha or A is equal to 0.05, same thing, level of significance, and I do not have the enough evidence available. So, this is two-tailed test which also confirms the same result, and if you go by the p-value approach you will see that this is the region which is larger than my significance, say assumed significance level, which is alpha, and it falls in the acceptance region. So, I will not reject the null hypothesis. So, sometimes it may sound little bit confusing, but the logic is very simple. By chance if you have a confusion, just revisit the steps proposed right at the beginning of this lecture and also in the previous lecture, various steps to be followed in hypothesis testing, and you will have a very clear idea. So, what is now the confidence interval approach? We have already seen. Suppose if I say null hypothesis mu is equal to 35, 95% confidence interval. So, I want to see that if 35 were within the confidence interval, we could conclude that the null hypothesis is not rejected at the given level of significance. So, this is another approach, as I mentioned, for checking or testing my hypothesis, and here for the example which we are discussing, that how much gram of cereal I fill in a particular box. So, x bar is equal to 372.5, sigma is equal to 15 or S is equal to 15, N is equal to 25. So, 95% confidence interval if I constitute, then it would be x bar plus or minus k sigma. So, here my k is 1.96. I have already discussed this part, and here sigma by root n, because I am doing it for sample, I am going by the central limit theorem, and this is my x bar. So, my confidence interval comes out to be 368.62 less than or equal to mu less than or equal to 378.38. So, if this interval contains the hypothesized mean, this is 368, which is true, we do not reject null hypothesis, it does do not reject. So, 368 is within this interval, and at a given level of alpha I will not reject my null hypothesis. So, this is something that we can do either through critical value, through p-value, or through confidence interval, and we have seen this. Now, we have a situation when hypothesis testing to be done for a single mean using t statistic. So, you have t distribution, and same way you have t statistic. Typically this kind of test we conduct for a small random sample having less than 30. So, let us say the t statistics is x bar minus mu divided by your S divided by square root n, and population is normally distributed, and if not normal requires a larger sample. So, we have the example, same example I may continue, and here what I say that does an average box of cereal contain more than 368 grams of cereal? A random sample of 36 boxes showed x bar 372.5, s is equal to 15, and you test the hypothesis as 0.01 level of significance. So, these are my alternate and null hypothesis, and I want to test my claim against this. So, I am just repeating the same procedure, but here I would be using the t statistics, and you can see very well that my alpha is 0.01, n is 36, degree of freedom is 35, n minus 1 I explained that I have one less degree of freedom to maneuver, critical value is 2.4377, and my computed value, critical value with respect to critical value is less, which is 1.8. So, my conclusion is that no evidence that true mean is more than 368. So, procedure is same, only thing here I demonstrated the application of t statistics, and you can say conveniently use it. Similar way you can apply the p value approach for even the t distribution and check. So, here again it falls within this particular range, larger than my yellow region, this yellow region. So, it is in the acceptance region, and I cannot reject my null hypothesis. So, hypothesis testing we can also do for population proportion. Typically, when I say this kind of test, it mainly includes the categorical values. So, you have two possible outcomes, typically success or failure, and I would like to express it in terms of the fraction or proportion of success, and typically category is denoted by p. So, PS is equal to x by n, number of success divided by sample size, and mu PS is basically p, and sigma PS, these are the things basically you need in order to compute the test statistic. So, sigma PS for sample is equal to square root of p 1 minus p divided by n. So, the question is like this: a marketing company claims that it receives 4% responses from its mailing. To test this claim, a random sample of 500 were surveyed with 25 responses. Check this claim at alpha or a is equal to 0.05 significance level. So, you just need to compute couple of things, NP, which is 500 into 0.05, so 20 greater than or equal to 5, n 1 minus p is 480 greater than or equal to 5, and now say I would like to test the hypothesis. So, just see this, I have the region available here, p is equal to 0.04, that is the claim of the company, p is not equal to 0.04, my alternate claim hypothesis alpha is equal to 0.05, I conduct two-tailed test, so it is divided, this is divided into 0.025 and 0.025, the corresponding critical value is 1.96, and this is my region, which is basically the reject region, which is 0.025. So, when I compute the Z statistic for proportion, I get the value 1.14, and this 1.14 is less than 1.96. So, it is in the acceptance region. So, I will say we do not have sufficient evidence to reject the company claim of 4% response rate. So, this is for proportion, and again same way I am not going into detail, but you can do it for p value. So, let us try to end this session with some think it, so that you can introspect, revise. What are the key steps involved in hypothesis testing? This is very important. Once you understand this, then whatever test statistic you need to follow for a given situation, you can execute hypothesis testing very easily. What is the difference between one-tailed and two-tailed hypothesis test? Explain the relevance of each one with suitable example. What is the difference between critical value and p-value approach? What is the key difference between Z statistics and T statistics? And what is the key feature of hypothesis testing for population proportion. Please use this book, Azell and Levin. I in fact referred couple of examples from this book, and that will help you to enrich your concept and understanding. So basically, hypothesis testing is the assumption that we make about the population parameter, and scientifically we try to check it at a given level of significance alpha with the consideration that I may commit type 1 and type 2 error. So thank you very much for your interest in learning hypothesis testing. Keep revising the various topics. We are going one after another in our Six Sigma journey. Be with me, enjoy.